Hi, thanks for joining us today. My name is Calvis Rice, and I am the Director of Business Development at IPS, Integrated Packaging Solutions. And the topic of this presentation is going to be a new approach to can weight control. So before we get started, I want to tell you a bit about IPS. So IPS is a company based out of Wheat Ridge, Colorado in the United States, and we have three distinct areas of our business. The first one is services. We provide equipment support, line control, oven support, and we also perform can line audits focused on reducing spoilage and increasing efficiencies. We provide these services for large can makers as well as independents all around the world. The second division of IPS is our products division, where we have a number of unique product lines. One of them is our tool surface finish product line, where we do things like crosshatch and polish tooling. We also have tooling inspections. So we've just released our ToolScan 2.0, which is a bodymaker punch and die inspection gauge. We have another product line focused on washers and ovens. We also have two pieces of software. One is a tool tracking and inventory control software, and we also have line monitoring software. The third area of IPS is our innovations department. And so the innovations department does product design for ourselves internally as IPS, and that's what helps us develop our product line. But we also provide services for customers. Typically, customers that are resource limited come to us and we help them with things like equipment design. We've helped them with prototypes, proof of concepts, and testing. So to get into today's presentation, let's all get on the same page of two goals. Number one, we want to make more cans. And number two, we want to better control our can weight. And so this presentation will focus on better controlling can weights through tooling factors. And so there's three tooling factors that we want to focus on. One, tooling dimensions. Two, inventory control. And three, tooling selection. So the first one we'll talk about are our tooling dimensions. And so when talking about tool sizing, it is extremely important to maintain a consistent baseline. And what that means is that if we measure our tooling day after day, week after week, year after year, we want that tooling to measure the exact same thing because our progression chart relies on that. The progression chart that we use in our body makers needs a reliable baseline of measurement so that the tooling works like it's supposed to and produces the cans that it's supposed to inside of the body makers. But it's not that simple. Baselines have a lot of factors that can affect it. So some of the variables that affect measurement baseline are the gauge. It all starts with the gauge. So not all gauges are created equal. Some gauges have different repeatability. Some gauges have fluctuations. Some gauges have better accuracy. Other ones have better usability. Other ones have different interaction when it comes to the user that's using the gauge. So the gauge is a large variable that can affect measurement baseline. Measurement temperature. So temperature changes, tool size changes. It is a variable to consider. Calibration standards or masters. So different masters used on the same gauge or on different gauges will produce different results. So in the ideal world, all masters are exactly the same, measured at 68.5 degrees. However, in the real world, there's small fluctuations in the actual reported values of calibration standards. So the master itself is something that affects a baseline. User error, that's a large component of a measurement baseline is user error. And finally, the measurement process. So the measurement process that is used to generate measurement of tooling is something that can affect baseline. So in the ideal world, for a stable measurement baseline, we use the same gauge in-house, a repeatable gauge, to measure absolutely everything. So if a vendor provides you with tooling that is new or reground and it has a size associated with it, that's a great place to start. However, it's recommended to measure every piece of tooling at a stable temperature with the same gauge before putting it onto your shelf for inventory. It's also recommended to always consider temperature. So that either means to calibrate a machine if temperature has changed, or it may mean other things, but it's important to always consider temperature's effects on what you are doing when measuring tooling. It's also recommended to eliminate user error as much as possible, and it's recommended to use a pre-measurement validation process when measuring tooling. And we'll go into what exactly that means here in a moment. So this time I want to introduce our brand new body maker punch and die measurement gauge, which is the ToolScan 2.0. And it measures ironing and redraw die IDs. It measures punch ODs along with the step and the taper. And it also measures punch profiles. So it does a scan of the punch profile. So two things that we really focused on the ToolScan 2.0 design. So the ToolScan 2.0 is actually a second generation machine. The original ToolScan has now been in the industry for about 5 years. And so in the redesign for our second generation machine, we focused on performance and we focused on value. And from a performance standpoint, the repeatability is unmatched in the industry. So 15 millionths of an inch or 0.38 microns repeatability, there's no other gauge that can do that in the industry in 15 seconds. So the 15-second measurement time, or under 15 seconds actually, for punches and dies is just an amazing feature. It also allows you to never have to change out any fixtures for either punches or dies. So the fixtures are designed in such a way that they can accommodate any of the production size tooling that you may need to put inside of it. So from a performance standpoint, the repeatability and speed of measurement is unmatched in the industry. There's also integrated temperature probes. And so these temperature probes do two things. One, they match the temperature for which the machine has been calibrated at. And so calibration is at a given temperature. And so if a measurement is about to be performed and the current temperature is different significantly from the temperature at which the gauge was calibrated, there is a big red flag that says, hey, it's time to calibrate again. The other thing that we're doing with those temperature probes is we are developing a temperature compensation algorithm for our software. And so this is going to allow the ToolScan 2.0 to take into account and compensate for small fluctuations of temperature, and that will stabilize your measurement baseline even further. And the final piece is that the ToolScan 2.0 has been designed in such a way that it will integrate with the tool control software. And so the tool control software, we'll talk about it here in a little bit, is our tool tracking, inventory control, and process control software. So talking about performance, there is nothing more important than speed and repeatability. And so here's a short video that I'll show you, and I won't click play quite yet because it's so fast. And so we'll show you that putting a punch into the ToolScan, it's going to do three things. It'll measure 3 different locations. It'll report back major diameter. It'll report back step, and it will report back taper of the punch. And you'll also see how easy it is to load that tool into the fixtures. So as you see there, the punch is easily loaded into the fixtures, and once you click go, it's going to measure those 3 locations. And so I believe a punch measurement here took about 10 seconds, and die measurements have gotten down to about 12 seconds. So that's speed and repeatability of this new gauge. The other piece we talked about eliminating user error is that because the tool scan is designed to be integrated with the tool control system, we focused on using 2D barcodes and marking tooling with these barcodes. And so by using a barcode scanner and integrating tool scan with the tool control software, we eliminate one of the causes of human error, which is transcribing a measurement onto the tool. So in this video, we're going to show you exactly how it looks putting a die into the machine, scanning it, and then that scan is going to tell our machine exactly what tool is inside and being measured. It's also going to, with that scan, select the right calibration group to apply to the measurement. And then once the measurement is taken, that same information with that serial number and with that measurement can be transported into tool control so that the correct information is always in the database. So we talked about baseline before, and we talked about the process for maintaining a baseline. And so most plants know exactly how to calibrate their gauges. And so calibration is something that every plant is going to do. However, a lot of plants don't realize that there is a need to validate after they calibrate. And what that means is that there can be a bad calibration, and unless you have a mechanism to identify whether the calibration is good or bad, you may have a bad calibration and measure tooling with bad values until the machine is calibrated again. And so the validation process assures that your calibration is good. So after the validation process, we recommend that the tool is measured. Now, after measurement and before any other measurement, we always recommend that you validate again. And so the ToolScan 2.0 has the temperature probes integrated into it. And so the way that we automatically validate before every measurement is to check the temperature at which we are going to measure and compare that to the temperature at which the gauge was calibrated. And if those temperatures are close enough within our tolerance level, then we go ahead and measure again. However, if the temperature has changed, our validation process says it's time to calibrate again. And so that's what we do. So the validation piece is an important component of the measurement process. So the last piece of can weight control, or the next piece of can weight control that we want to talk about here is inventory control. And so it's very important to state here that the most important role of inventory is to support production. And so what that means is that if you have a tool pack inside of your body maker, it is critical that the sizes are also available on your inventory. So the worst thing in the world would be to install a brand new tool pack into a body maker, have to change out a third ironing die for whatever reason and not have that size available. Because if that size is not available, then you have to pull out an entire tool pack. And so the important part is that inventory supports production. And so flexibility is the key piece here. So obviously the entire tool pack must be supported on the shelves, but we have to have two things available. One, the nominal sizes in inventory, so exact replacements of tooling, but also it's important to have the ability to move up and down in sizes to give the operator a little bit of flexibility in what they're doing. And this is obviously most important in the third ironing die. So when you have flexibility, the ability to move up and down, and when you have your inventory supporting production, you're actually maximizing your tool life, because by changing individual tools, you allow your entire tool pack to remain in the body maker a lot longer. So tool control is our tool tracking and process control system. And so tool control is designed around 3 modules. The first one is the base module, which has an inventory control component. It has tool tracking capabilities, and it also has a grind schedule. And so when we talked about the most important role of inventory is to support production. The grind schedule allows for us to do this because it prioritizes what is currently in production and says that we have to make sure that inventory has the appropriate sizes. And so it takes it a step further and it says exactly which sizes need to be ground, but it also tells you how many of that size need to be ground so that we're not wasting any grinding resources. Tool control also has a reporting engine which allows you to run lots of useful reports. The final piece now of can weight control from a tooling standpoint is the tool selection process. And so when selecting tools, we want to use data because if we use data, we're able to make better decisions. So at the beginning of this presentation, we had 2 goals. 1, make more cans, and 2, better control our can weight. And so by tying back in QA data and saying that the can weights previously were this or the can wall thicknesses were that, we're able to use that data and say which tool sizes we should be changing out in our body makers. So that brings us up to the other modules of tool control. We already talked about the base module, which is inventory, grind schedule, and reporting. But now we'll talk about the production module. And the production map module ties in your production body maker data with the tool control system. And the third module is the can weight module, tying in your QA data to the tool control system, specifically can weight and wall thickness data. And so what I'd like to do now is look at the tool selection process through tool control. And so we start at a production body maker, and we know we have to change out a tool. And so we move to the tool selection module. And as we talked about before, data is key here. We want to make better cans and more cans. And so what data do we actually need to better control our can weight? It's the QA data. So by tying together the QA data and putting it front and center in the tool selection process, we can decide exactly what size tools we should be now putting into our body maker or changing out into our body maker. So that's great. We know exactly what size we need. The next piece is the grind schedule. So the grind schedule supports inventory and makes sure that inventory has the right tools on the shelf. And so the next piece is that the tool selection process says we need these tools and inventory has those tools available. So we select the right tool at the right time and we now put those into the body makers. And with data, we can do 2 other things here. We can start making predictive changes. So with production data, stroke count from the body makers, we can start identifying patterns, right? So if, for example, body maker 3 starts having tear-offs after X number of days, we can start setting predictive alarms to change out a tool before a problem actually happens. The same type of thing we can do with the QA data. If we start seeing on body maker number 5, for example, that the can weights start going out after X number of days, we can start setting triggers that before that ends up happening, we know that we have to change out tooling. So data is so important in the general function of our tool control system. The last piece of information that I want to share is this graph here, and it really demonstrates a can weight savings opportunity. So what we have depicted here is the can weight distribution of two different plants. So the orange line here shows the distribution of a very well-running plant. And that means that the majority of our cans are right here at the center, and as we move to the left and to the right, the distribution, there's fewer of these cans, meaning that this line here, which represents the minimum can weight accepted by a customer, there are not many cans that are at the minimum weight, because we want to make sure that there aren't any below the minimal weight. So this orange line represents a well-running can plant, and the blue line represents a poorly running can plant. So likely there could be many causes for this, but not changing tooling to the right sizes and not paying enough attention to where the can weights are can be a contributing factor. Of course, this assumes that your body makers are aligned. But what this graph really represents is that these are two plants running the exact same can, and one of the plants is running better than the other. And so the savings opportunity there is represented in green. Now, over the past few months, we've analyzed a number of customers running same size cans at different plants, and we've identified savings opportunities as much as 20 cents per 1,000 cans. And so by putting QA data front and center in the tool selection process, there is a large savings opportunity when talking about can weight. And tool control allows you to connect that data with the tool selection process. So we talked about two main products today, and the ToolScan 2.0, it's available now. We just released it about 4 weeks ago, and we're currently giving live web demos of the equipment. So if you're interested in seeing more about this piece of equipment, we can schedule things remotely for you and your team. It allows you to see the equipment live. It allows you to ask questions in a setting where you get all of the information taken away right there. But the ToolScan 2.0 is available now, and the tool control, we're currently scheduling our plant trials, which are expected to take place starting June of 2019, after which in the summer of 2019, we will be releasing the tool control commercially. So that concludes our presentation. Thank you very much to the CanTech International team, and thank you all, the 2019 attendees.